Okay, good afternoon.
It's now 2 p.m. and I think we can start. So, Gordon.
Everybody to this Science Festival presentation, where Jan Tomec and Konstantina Ntarladima will present you what they are engaged with within the European Horizon 2020 Marie-Sklodowska-Curie Action Joint Training on Numerical Modeling of Highly Flexible Structures for Industrial Applications. Jan is our PhD student at the University of Rijeka, and Konstantina is our guest. And more about why she is here and how it fits within the project, you will hear on the presentation. So, Jan and Konstantina, please.
Thank you.
So we'll start the presentation now.
Can you just move this? Okay. So hello, our names are Konstantina and Jan, and today we are going to present to you the European Research Project THREAD. We began working on the project less than half a year ago. To describe the project in a few words, we can say that THREAD combines the research in engineering and mathematics to seek for new solutions on simulating highly flexible structures. Motivation for this project comes from the industry. Structures like cables, ropes, and hoses are difficult to simulate because they are non-linear. They also lose stability when we compress them. These structures are usually lightweight. This usually results in higher frequency of the response, which causes additional difficulties when modeling. Such structural elements can be found almost anywhere and have a broad field of applications. Cranes, bridges, hydraulics in cars and robots, drilling systems, and on and on. They are also used to simulate ropeways in cable cars and antennas in satellites, about which we will talk to you today. Currently, the simulation of flexible cables, rope, and hoses provides only an approximation of the real system, or get numerically unstable, which means that the results are not useful.
THREAD network joins together 11 universities and one non-academic partner to collaborate on 14 different research projects. Each institution employs 1 to 2 early-stage researchers to conduct research on a certain topic and work simultaneously on their doctoral study. These projects join together into work packages with common topics to further collaboration. THREAD is funded by the European Union's Horizon 2020 Research and Innovative Program, and it is conducted in close relation to industry via several industrial partners. This can be seen on the map as red dots. White dots are represent the universities and the industrial partners, CITRIAN. Industrial partners are an integral part of THREAD and help with real-world experiences from the industry. This helps us, the researchers, to gain a better understanding of the relevance of our research and how the academic theories are implemented in practice. It also gives us an insight to the organization and work in a company. Industrial partners, on the other hand, receive early insight into cutting-edge research, get contacts with academic partners, including us, the researchers, and they get a chance to define specific industrially relevant topics of research in this field. There are 14 researchers in THREAD, and we come from all over the world. I am, for example, from Slovenia, while Konstantina is from Greece. Most of the researchers come from European countries, however, we also have a few from other continents, specifically North America and Southwest Asia. On the map, you can see the origin countries in dark blue and the host countries in light blue. The aim of the THREAD project is not only to conduct scientific research, but also to educate young researchers to become independent and successful in their future careers, either in academia or the industry. Therefore, we participate in industrial and academic exchanges to further extend our knowledge on the subject. We call such exchanges secondments, and they help us to meet other researchers. On the map, you can see academic institutions in red dots and industrial partners in blue dots. Each researcher goes to one industrial secondment and usually, but not all, also go to a couple of academic secondments. Besides this, we also engage in different training events organized by the participating institutions in THREAD to develop a wide range of skills, from theoretical knowledge to soft skills like writing and presenting and industrial workshops.
The first training events have already taken place. In this summer, 2 conferences were organized. They took place online because of the corona crisis. However, active participation and direct communication were 2 common points of these events. The first training was organized by Friedrich Alexander University. Its topic was the fundamentals of bit theory and flexible multibody dynamics. It was aiming to give us the basic theory on THREAD field of research. During this event, we interacted a lot, both with the lecturers and with our colleagues. We also worked in teams on trying to solve problems that were posed to us during the evenings after the lectures. The second network-wide training event was organized by the University of Ljubljana. Its title was Learning about Scientific Writing and Communication Skills. We were given a lot of useful tips about writing strong scientific articles in English. It was emphasized that composing a good text depends on the language you're writing in. So, as we come from different countries all over the world, some guidance on how to use efficiently English language was very useful. We also took pieces of advice about speaking in public with confidence. Most importantly, we had the opportunity to meet and get to know each other. The first real-life training event took place in Austria in the first week of September. We finally had the opportunity, the most of us, to meet in person. It was also covered online for the participants who were not able to come. We all had the chance to attend a sequence of scientific lectures regarding the choice of coordinate formulation for the modeling of roadway systems. Advanced numerical methods and simulation techniques were presented. Fundamentals in the mathematics of Lie group theory were also shown. In addition, a challenge was posed to us for which we had to collaborate and make a presentation at the end of the week. Of course, we didn't lose the opportunity to explore the surroundings and do some hiking in the mountain. I'm working in the University of Innsbruck under the supervision of Professor Johannes Gerstmer. Our industrial partner is an Italian company, Leitner. Leitner is one of the biggest manufacturers of roadway systems. I'm going to work there for 3 months during my employment. In that way, I expect to gain some experience in working in an industrial environment and to see the real-world application of the theory I am studying. I will also spend a month at the Mathematical Research Institute Fraunhofen ITWM in Germany. Finally, I will be working for 1 month in the Martin Luther University, Halle-Wittenberg, also in Germany. Modeling and simulation of roadway systems can be of important essence for multiple industrial applications. In specific, cable cars and lifts equip every ski resort and an incident to experiencing every winter sport. Industry related with the production of this construction continuously work on improving the quality, the technology, and the design of roadway systems. Sometimes cable cars are also used in cities. They are used by the general public, for example, elderly people. This is why the ride needs to be very smooth. To be more specific, the oscillation needs to be kept small in order that people accept such transportation systems. The same is true for ski resorts, perhaps in a little smaller extent. Different types of cable cars and chairlifts exist to make passenger experience both entertaining and safe. However, to design these systems appropriately, we need a lot of research. The mathematical modeling of such slender structures requires the implementation of a sequence of methodologies and computational tools. My research topic focuses on modeling and simulation of cables with transported mass points. In the case of my industrial application, the transported masses are the vehicles that are moving along the cables in roadway systems. The main goal is to develop an efficient model for simulating such a system, taking into account its geometry and properties. The contact with the sieves needs also to be modeled. Another goal is to contribute on the development of an open source code. The coding should be organized in such a way to be handleable and useful for modeling different flexible and slender structures. As far as our current approach is concerned, we use beam finite elements to simulate a rope. The types of beam elements that can be used for this are the geometrically exact beam element and the absolute nodal coordinate formulation. The former was initially implemented by Simon and Vukok in 1986. This type is chosen because it is comparatively simple. Two nodes are used for each element, which are interpolated linearly. On the other hand, the absolute nodal coordinate formulation is already used for modeling a roadway system, as it is convenient for thin structures. Two nodes are used again for each element. The interpolation takes place with third-order polynomials. Absolute nodal coordinate formulation is convenient for problems on which there are large deformations, such as thin cables and ropes. The studied structure can be approached either. Sorry, I have a simulation here.
Just a second to set up the simulation. So, okay, so you can see now the simulation.
Okay, I hope that now you are able to see the simulation. The studied structure, as I said, can be approached either as a continuous moving mass or as discrete masses that are moving along the cable. In the second case, the movement of discrete masses can cause instability. And I hope that in the left of the slide, we can see the simulation of a moving belt with transported mass points. Watching this behavior for increasing axial velocity, we observed that oscillations get very large and we have resonance. It is evident that a finite element mass is needed at the points where the rope is in contact with the sieves, while larger finite element can be used in the free span. To deal with that issue, we use the so-called arbitrary Lagrangian approach. Using this approach, we assume that the considered beam finite elements do not move along the strip axis during the simulation, but keep a fixed underform configuration in time. In what follows, I'm going to elaborate a bit on our scientific approach and give an abstract illustration of the mathematical formulation. In the figure, R denotes the position vector of the beam and X is the arc length coordinate. The geometrical description of the used finite elements is purely based on displacement and does not use rotational coordinates for the cross-section. An element with 2 nodes is associated to 8 generalized coordinates. 4 are affiliated to its node, representing displacement and slope of the beam center line. The positions are interpolated with shape function, which can be written in a matrix form, as we can see in the slide. In this point, we introduce the equation of motion. The weak form of the equation of motion is derived from the Lagrange-Dalibard equation. It is a balance of kinetic and strain energy and energy due to inertial forces. For the definition of generalized forces, we need the axial and bending stiffness, epsilon A and epsilon I respectively, and we are left with the last expression that we can see in the slide. The already described element can be extended to the case of an impressed constant axial velocity. This way, an axially moving beam is modeled by elements which do not travel at the impressed axial velocity, but keep their axial position relative to this velocity. The Lagrange reference configuration of such an element is then moving through the strip in negative direction in the prescribed velocity. The velocity of a point on the beam axis is given by the derivative of the position vector defined in the Lagrangian reference configuration. One can note that the velocity vector does not only depend on the time derivative of position, but also on the spatial derivative of position. Although the formulas look complicated, what is important to point out here is that if we consider the additional inertia forces and do the appropriate substitution in the equation of motion, the absolute nodal coordinate formulation beam element can be extended for an axially moving rope. Programming occurs in an already existing software, Exodyne. Exodyne is developed at the University of Innsbruck. Most of the code is written by my supervisor, Professor Johannes Gerstmeier. It is a C++-based Python library, which means that the user has the possibility to call existing commands in order to set his system. It is useful for modeling flexible multi-body dynamical systems. Multi-body systems are systems composed of various rigid and flexible bodies. Exodyne offers the possibility to the user to easily set up systems composed of rigid and flexible parts, loads, and other components.
Hi again. I'm stationed in Rijeka at the Faculty of Civil Engineering under the supervision of Professor Gordan Jelenic. My project has this title, Stable Long-Term Numerical Integration of the Cosseret Rod Problem in Large Overall Motion. To explain briefly the meaning of my topic, numerical integration is a tool we use to see the evolution of objects' movement in time. Here the object in question is a beam or a rod. Its geometry is explained with the Cosseret rod theory, where we use for description the position of the center line and the rotation of the cross-section. The motivation for my project comes from space technology. As there are more and more small and medium-sized satellites orbiting the Earth, it is the trend trend today to send multiple payloads at once with a single rocket. On the scheme, you can see an exploded view of the European Space Agency rocket Vega. And here, oh, this doesn't work. Okay, so maybe like this, yes. Here you can see the payload module. This is the same payload module that actually carries the satellites, and you can see this is the entire capsule and this is the module with satellites, and you can see how cluttered the space is, and you can imagine that it is convenient to make satellites smaller to save space. This is the same module without the capsule, and here is a satellite from the company where I will attend my secondment, NEMO HD. It was sent to space a few months ago. It is also, this company is also a part of THREAD. And here you can see enlarged image. It is already mounted to the payload module of the rocket. And here you can see the backside of the satellite. And you can see these antennas. And the idea is to save space by bending these protruding antennas. However, this requires careful dynamic analysis to avoid any damage during the launch due to the high frequency vibrations and impacts with the surrounding objects. On this picture, you can see the inside of the satellite. The majority of the space is taken by this camera, while the rest is electronics. It also needs to be carefully designed to withstand the extreme loading scenarios during the launch. However, this might be a subject of a later research. In the next 3 to 4 slides, I will dive a little deeper into the theory. So generally in mechanics, we have two sources of nonlinearity: material arising from the properties of the materials used in the application, and geometrical, which becomes evident in applications where we deal with large deformations of a structure. Today we will focus on the latter, particularly on geometrically exact beam theory. This picture tries to explain how the deformed geometry of a beam is connected to its undeformed state. We will not study it now, however, we can observe that there are two parameter groups needed for a full description: displacements and rotations. Displacements are more or less straightforward in terms of the computations, as you can add them simply with summation. However, rotations are a little trickier, as they are, mathematically speaking, part of special orthogonal group of transformations, which is part of the Lie group. If we account for these facts correctly, we can derive the kinematic equations connecting the deformed and the undeformed state of the beam. However, this is only the first part in the mechanical analysis of a beam. Now we need to explain how the object moves due to the forces acting on it. Here we resort to the almost 300 years old Newton's laws of motion, which state that the sum of all forces applied to the rigid body is proportional to the mass and the acceleration of this body. A beam is, however, a flexible structure, which requires from us to apply this theory to every material particle in it. We gain two equations, one for the conservation of the linear momentum and one for the conservation of the angular momentum. In the final step, we join these balance equations with the kinematic equations via the constitutive relationship. This is a relation between the stress and strain, or forces and deformation, if we simplify. It is a material property, and in my research, I use the simplest possible material model, which uses only two material parameters and connects the forces to deformations linearly. This is true for materials like steel. When we join all these equations together with a mathematical tool called variational principle, we gain a finite element. When we analyze a structure, we divide it into a whole mesh of such elements. An example is on the picture, where you can see a straight beam divided into 4 elements. Last, we have to introduce boundary conditions like displacement and supports and forces, and then solve the system using another mathematical tool, iterative solver like Newton-Raphson method. When I coded all this theory, I created a software that can numerically analyze beam structures. An example is now presented to you. It is a straight cantilever beam. Here you can see it. It is loaded with a force and with a bending moment. And on the bottom picture here, you can see how it rolls into a helix. And this, on the animation, you can see the evolution of the solution of the system through time. And in the second example, is a right angle frame loaded with the two opposingly oriented moments, here and here in supports. And this represents a stability problem because when we apply a large enough bending moment, the stability collapses and it bends in this way, how you can see on the animation. Finally, the goal of my project is to develop higher order interpolation and not limit ourselves to two-node elements. We will investigate different conservative time integration techniques for dynamic analysis. They have to be capable to account for high-frequency vibrations and large overall motion. We will study the effect of unilateral boundary conditions, and we also want to validate our model with experiments. This was our presentation. We thank you for your attention. Before we go to any possible questions, I would just ask you if we can take one picture together. Stop share. Okay. Here we go. Okay.
Maybe another one as well.
Okay, one more. Okay, so now we're available to you for your questions.
Well, maybe I would have one question. Hopefully it's enough accurate. So what do you expect to obtain by using an element with more nodes and higher interpolation functions? Just accuracy or something, some other improvements?
Yes, we expect to get to improve the accuracy of the solution while reducing the time of the computation, and also it is important for the time analysis, because for dynamic analysis, because of the high frequency vibration. So we need to improve the accuracy for each step to have a longer stability in the solution.
Okay, so if there are no more questions from the audience,
Dragan, we can turn on the mic and give a...
Yes, I want to say that you deserved a clap for a very good presentation, but unfortunately everybody has their microphones off, so it is a virtual clap, let's say.
We can turn on the mics.
Yes, we can do that.
Okay, so we thank you all again for your audience and yes.
Yes, thank you very
Jan.
much.
Thank you, Konstantina.
Thank you.